The next most common is a fat sarcoma called liposarcoma, where Jonathan's laboratory and others across the world have wonderful insights trying to figure out how we can target that, and then a variety of others. So how do we use this knowledge, and how do we go microscopic and try to get better therapies for different kinds of sarcomas, therapies that are effective and safe? And the first thing, the obvious that you've heard all day, we need to recognize that GIST and other sarcomas are different in different people. There is no one-size-fits-all for cancer. There is no one-size-fits-all for GIST, and there's no one-size-fits-all for sarcomas. So that really means we need to offer personalized therapy, to use the right expertise and to pick the right treatment, sorry about the typo, the right treatment at the right dose for the right type of GIST or other sarcoma in the right patient and at the right time of the disease. It's a lot of rights. There's a lot of things that could go wrong if you do it wrong. And here's where the power of the collaborations are really coming together. We are so proud at Dana-Farber Cancer Institute to have partnered with the Brigham and Women's Hospital in what we are calling the Personalized Cancer Medicine Partnership, which really will be an incredibly cool research effort where our trustees have given us a lot of money to do this for free to patients, where we can do extremely complicated gene profiling to see if there are other mutations that are causing cancer. Every patient, starting sometime this year, will have the opportunity to sign up to have these sophisticated genetic tests done for free, not charged to their insurance company, as a research trial, so that we can see if there are other hidden mistakes in the genes of people with cancer. A remarkable opportunity to learn a lot and potentially identify other actionable information. Actionable information is a popular term these days because of the intelligence community, but we do feel like that's what we need. We need actionable intelligence to go after the right targets in cancer. So what's our next strategy? Well, we want to get more great results. This field was blown wide open because of the kind of collaborations we were lucky enough to have, and because we were fortunate because we understood this disease. And you've seen a lot of curves today. Let me just say, on the bottom here's a timeline. If we're tracking time in months or years or whatever on the bottom, and over there on the y-axis it says overall survival, well, if you start with 100 people and they're up there, what we really want is that all 100 people stay alive, so the curve should look like that. It should just keep going across the top. What we knew about GIST, unfortunately, once it was advanced in the old days, prior to the year 2000, is that the survival looks something like that. And every time the curve goes down, somebody has died from the disease. So that what this means, 0.5 survival, means half the people have died in 6 months. That's pathetic. And virtually everybody died by 2 years. Now, somebody's still alive out here in the old days, partly because they probably had that pediatric or wild-type GIST, or the neurofibromatosis type GIST, which tends to be something of a slower-moving disease. But that's still an awful survival curve. But we knew that, and the exciting thing was as soon as Gleevec hit, because we targeted to the right patients at the right time, this is what the survival curve has looked like now over the past decade, where half the patients can look forward to at least a 5-year survival, and a lot of the patients can look forward to more than that. About 20% of patients are still alive more than 10 years later for a disease that used to kill people reproducibly within 6 to 8 months. That's a massive improvement in survival. There was no question this was great. But when I say we don't want to sit on our laurels, to us that's not good enough. That is just not good enough. That means half the people are not living for 5 years, and virtually nobody's being cured. How would you like it? We always think antibiotics are great things, right? You get bronchitis, go to the doctor, get an antibiotic. 4 weeks later, you're cured of your bronchitis. How would you like it? If you got an infection, you went to the doctor and say, oh, you got an infection. Here, take this antibiotic for the rest of your life. Go ahead. Your infection will be controlled. I guess it's better than dying of your infection, but that wouldn't be a very compelling antibiotic. And that's kind of the way we feel about all the drugs we have now. Gleevec, Sutent, good drugs. They're keeping people alive, but you have to be on them forever. That's not a cure. So we have our work cut out for us still. And that's the key question that Jonathan and I and others are asking. Why are we not curing more patients with GIST? If we understand it so well, it must mean that as well as we understand it, we don't understand it near well enough. And that's why Jonathan and Adrienne and other people are probing the biology much better. And that's why we're so interested in ripping this apart down to the DNA and the molecular level to understand this actually happens to be the KIT protein. And we can structurally see it in 3 dimensions, kind of like a little Lego toy. So we can see just where the vulnerabilities are. This little blue thing in here happens to be Sutent bound into that binding pocket. And we can see how different variations affect how the drugs work in this. So the key question, how do we shut these off even more? A lot of people have been saying, okay, so you get this mutation and then it becomes drug resistant. Let me just show you a little bit, just a couple of pictures, because I like Legos, okay, and I'm a simple-minded doctor. So I kind of like the idea that here's a normally controlled, normal KIT. This is what KIT in my body looks like. And by the way, everybody's got KIT. You need KIT to make your hair color, you need KIT to make your skin color, and you need KIT to make normal blood cells. So you need normal KIT, and it has to be controlled normally. What you see is a part of KIT, and these blobs here show something interesting. There's 2 green blobs there. That green blob that's pushed to the left means that this enzyme is off. It's not functioning like a light switch in the on position. If that green blob's pushed to the left, the thing's off. Here's what happens if you have a mutation. That green blob has moved to the right. See this thing right here? It's moved in, and it almost looks like it's stacked up, kind of like a bunch of poker chips or whatever. You know, it's just stacked up in one area, or like we like to say, like a spine. It almost looks like the vertebral column in the spine. And that means the KIT is turned on. Now, here's a cool new set of drugs that are just being developed. Jonathan and our close collaborator, Mike Heinrich, out in Oregon, and I and others are working on developing this as quickly as possible because we think it could be a game-changing type drug. And the drug is this blue thing in here. The blob basically goes in, takes up that space, and pushes, again, that green thing out and shuts it off. It works through a different mechanism than Gleevec or Sutent or nilotinib or sorafenib or regorafenib. It's a totally different class of drug. So we are very excited about picking this and seeing if we can take it out on the road and see what it can do. If drugs were a car, you always want to take a test drive. And I think Dr. Butrinsky gave you the sense that the patients are on the front line of those test drives that we need to do safety. We need patient participation in clinical trials. We can't do our own test drives. It's a partnership. We can drive it only so far, but then the patient participants, the volunteers, many of you in this room, have to take these things the next 500 yards so that we can make real progress in the field. And then finally, let me tell you one other story, because again, Jonathan's just too darn humble to tell you this himself. The question of, are there any other great targets in GIST? Because I can only do my job as a clinical drug developer guy if I have great targets and great things to work with. And I'm lucky because I have a great team here. And my great team here involves Jonathan, who is a terrific collaborator in his laboratory, working with another one of the world's best scientists. This guy, Charles Sawyers, runs a program at the Memorial Sloan Kettering Cancer Center. And Charles, you'll see his name on this, Charles works with Christina Antonescu, a pathologist who's got a terrific interest in GIST at Memorial Sloan Kettering. Bob Mackey, again, a medical oncologist that we trained, who was at Memorial Sloan Kettering, recently left to go to Mount Sinai in New York City. And here's our old friend John Fletcher on this paper in one of the world's most prestigious scientific journals called Nature, with a really long title. Okay, it takes a long time to work through scientific papers titled ETV1 is a lineage-specific survival factor, la-di-da-di-da. What does it mean? Here's the story of this story, because I love this collaborative story. There was somebody in Dr. Sawyer's lab who got interested in prowling around the gene sets. You've heard about these gene sets, and Adrian just showed you a bunch of gene data sets. And they said, well, here's a bunch of sarcomas and GIST, and here's another bunch of sarcomas and GIST, here's another bunch. Look at this. All the GISTs seem to share this high-level expression of something called ETV1. Isn't that interesting? ETV1 is related to something important in prostate cancer. Is that really important for GIST? Well, then they looked at a whole bunch of different kinds of cells, breast cancer cells, bladder cancer cells, prostate, all sorts of other things. It turns out that GIST, this is GIST over here, GIST has the highest expression of this ETV1 stuff. And then they looked at it and they said, is that really true? And they looked again and they said, look at this. Here's ETV1 and here's KIT and here's ETV1 and here's KIT. And if you don't have GIST, you don't have this stuff. Isn't that cool? So really what this says is back to what Judy Garber was saying. Why do you get families who have mutations in KIT and they get GIST? Why don't they get, breast cancer? Why don't they get ovarian cancer? Why doesn't KIT cause cancers and other things routinely? And it's because of this stuff called ETV1. And it's a long story about this, but it turns out that these young cells in the gastrointestinal tract that, if they were normal, would be interstitial cells of Cajal, but when they turn cancerous or turn GIST cells, it turns out that these things have this ETV1 in it, and this KIT is very well controlled. KIT signaling goes through something called MEK. You've heard about MEK inhibition in Adrian's talk. And when it's dysregulated, this whole thing turns into GIST. So now we've got KIT going through a bunch of other intermediary pathways and ultimately being dependent upon this ETV1. Now, how cool is that? As we're looking for new targets, how about if we just take out KIT up at the top, take out ETV1 and down there, and take out MEK in the middle? And we've got a whole string of pearls of wonderful targets to go after. We are just about to start our studies with MEK inhibitors here, including opportunities for GIST patients to participate, so that's a possible thing. We've already got lots of things targeting KIT. ETV1 is a different challenge, though. ETV1 lives deep, deep, deep inside the cell and is related to transcription factors which bind to the DNA. There are other chemical challenges, but they're not above our chemical biology people and other great scientists to develop new tools to go after those. So I just wanted to show you where we're going, because this is really where we're going. Might combinations of drugs be useful to get better effects for patients? One of the audience members earlier suggested that. How come you're not mixing and matching things? And the reason is because many of the things we've got are too darn similar. You know, Gleevec, Sutent, sorafenib, regorafenib, they're all IBs, SIBs of IBs, as Bob Mackey used to say. They're kind of similar. In fact, my son, who's pretty smart but hard to impress, he says, "Dad, you don't want to just develop another kinase inhibitor, do you? Aren't you bored with them already?" And the truth is, he's kind of right. So that's why we're going after something more clever, something more creative, but also something more high risk. And that's where the kind of philanthropic support that the GIST Cancer Research Fund has provided to this operation has been absolutely key. And I'd like to thank Robert and Tanya and everybody else involved in GCRF for the tremendous and very, very important support for Jonathan's lab and for our whole program. And finally, I've just given you scratch the surface. I'm not going to bore you with real details, but the fact is there are all sorts of things we can block. We can block PI3 kinase, MEK I told you about. We certainly can easily block mTOR. And when we start putting this package together, we could potentially spend the next 20 years just doing the 5 combinatorial type trials I just put up on the slide. We don't have time to do that. None of us are going to be alive long enough to do that. None of you are going to be alive long enough. So we can't be happy with that. We are going to develop better ways of predicting in animals, in vitro, which means in the cell lines. We're going to predict better what clinical trials are most worth doing and then do the right ones fast. And that's part of what our whole game plan is, to move this ahead fast. Last thing, last slide. Patients are smarter and more enabled, particularly by the internet, than ever before. We think that's a blessing because we view this as a partnership with our patients' families. We want people to ask about clinical trials. Somehow, clinical trials got a bad name in this country. I have no idea why. I think patients should be begging their doctors to participate in clinical trials. We should be making it easy for people to participate in clinical trials. Instead, we seem to be setting up one regulatory barrier after another to patients participating. And what worries me a lot is with the healthcare reform that's going on, you never hear anybody talk about coverage for good quality clinical research trials. And I am so tired of hearing good patients who want to participate in our trials get denied by their insurance companies because it's not in their coverage. That's research. That's not care. We're only paying for care. We're not telling you what to do. You can participate in that trial, but we won't cover anything about your care if you participate in that trial. That is just a public policy disaster. And I don't see anybody in Washington standing up and saying, we can't be satisfied with that as a country. So I actually think, especially as the cost pressures go up and up and up in the near future, patients are going to have to advocate for themselves, that research is part of care and that we have to really see how we move this country forward and advocate for GIST and sarcoma care right along with breast cancer and ovarian cancer and lung cancer and colon cancer for the best possible care and the best possible research based on the best possible public policy we can develop in this country. So with that, it's my honor to say thank you, all of you, for coming out today and participating. Thanks so much to the GIST Cancer Research Fund for their support, and thank everybody here for all that you do. Thanks again on behalf of all of us.